Alright, this is the second half of another review of exponential and logarithmic functions. If you have a pencil in your hand, put it down. Watch me do it, learn it, and then go back and do it yourself. Jumping right in with problem number 1. When we look at a log problem and we're trying to evaluate, we ask ourselves the question, 625 to the what power is going to give us 5. Okay, always starting with that base. But wait a minute, you say, this is a big number. If I square it or cube it or something, it's just going to get to be an even bigger number, not smaller. Well, there is a kind of exponent that will make a big number smaller. No, not a negative power. That's just going to drop you down to the denominator. So don't say negative something. Oh, it's a fraction. It's a fraction. The reason why, if you look at the exponential table, 625 and 5. There's 5. There's 625. 5 to the fourth power is 625. Okay? That means the fourth root of 625 is 5. Did you hear me? I'm going to say it again. The fourth root of 625 is 5. This is what we need to happen. But the fourth root is the same thing as the 1/4 power. So that's what this x needs to be, the 1/4 power. Number 2. Now, there are many ways to do this problem, but no matter how you do it, it helps to understand that there's an invisible base 10 right here. Now, one way I taught you to do it was to ignore this 1 for a moment and go ahead and ask yourself the question. 10 to the what power is equal to 100,000. Count the zeros. 1, 2, 3, 4, 5. That's 10 to the 5th power. So you should be thinking at this point 5. Right? If you don't believe me about the counting zeros thing, 10 to the 5th power, kabam, 5 zeros. Check it out, 100,000. So far that would be 5, but it wasn't 100,000. It was 1 over 100,000. So this would need to be -5 to drop you down to the denominator like that. Kabam. Number 3. Oh, looky here. We have a big number turning into a small number once again. So when you ask yourself 4,096 to the what power is going to give you 4, you should be thinking to yourself, okay. What is the root that's going to turn this thing into a 4? You know what I'm saying? Is this going to be the square root, third root, fourth root? What's going to be? Let's check it out. Let's look for 4 and 4096. Okay, there's 4 and 4096. That is 4 to the 6th power. 6th power. That means the 6th root of 4096 is 4. 6th root. Okay, so that means the 6th root will get the job done, but the 6th root is the same thing as the 1/6 power. So that's what x would need to be. Anytime you see a bigger number go into a smaller number, you know it's going to be some kind of a fraction. Okay. Sort of an exception to that rule right here. It's going all the way down to 1. We all know what power will change an 8 into a 1. Alright, because we're thinking 8 to the what power is equal to 1. Well, anything to the 0 power is 1. So it would have to be 0. Do not ignore the P and leave it out. A lot of kids do that. That would be a mistake. I'm going to approach this problem slightly differently. The 27 is 3 to the third power. Okay, if you didn't know that, look at the chart. 3 to the third power, that's 27. So I could write this as log base 3 of 3 to the third power. Man, that's a lot of 3's. But don't forget the p though. P is up here in the exponent, 3p. Now, log base 3 and base 3, they undo each other. They're inverses. They cancel out. So that's just going to leave 3p. A lot of kids would just put 3, but that's wrong. Okay, that's one way to do it. For me, that's the easiest way to do that type of problem. You know, just to be crazy, let me point out to you that we could do some of these other problems the same way. Okay, let me show you what I mean. Take number 2, for example. I'm only going to do this once, but looking at number 2, this would be the same thing as log base 10 of 1 over, and like we said, 100,000 is 10 to the 5th power. But because it's in the denominator, wouldn't this be the same thing as log base 10 of 10 to the negative 5 power? Because wouldn't that drop you down like this? Yeah. But then, just like I did on number 5, if I have log base 10 and base 10, those undo each other. They cancel each other out. And that would just once again give me negative 5. So I could use this type of analysis on most of these problems. But on number 5, it is especially convenient. Okay, number 6, looking at the invisible base 10, we ask ourselves, 10 to the what power is equal to 10,000? Look at how many zeros it has. That's 4 zeros. That means this is 10 to the 4th power. So that means 4 must be the power. My favorite way to do number 7 is just like a couple other problems that we've already done. When you see 1 over something, you could just cover up that 1 and ask yourself the usual question. 2 to what power is going to give me 32? Now, I know that that is 5, but if you did not know that, you would look at the table and you'd see 2, and you'd look for the 32 and you'd see that's the 5th power. So 2 to the 5th power is 32. Okay, so far that makes you think that 5 is the answer. But it was not just 32. It was actually 1 over 32. So for that reason, it needs to be a negative 5. Because a negative power would drop you down to the denominator like this. Boom! Just one more video. Anyway, ask yourself the question. 3 to what power is equal to 243? Not sure. 3, 243, that's the 5th power. So, it's got to be 5. Plain and simple. Yeah, number 9, again, is one that I'm really going to want to do the way I did number 5. Okay, it's really just the easiest way to do it. There's an invisible base e anytime you have a natural log. That means I have log base e of e to the 5th power. Alright, log base e and base e undo each other. They cancel each other out. And that's going to just leave the 5 there. So that's why that is just 5. Alright, not e to the 5th, just 5. Okay, let's find number 10. Graph the following function and its inverse. For some reason, many of you are just ignoring this. Okay, you better not do this on the test. Graph the function and its inverse. Goodness, I feel like only like 6 people are actually following these directions. After blowing off remember that homework that you got on the day school was closed because of the ice? Only like 5 people did that assignment properly. The rest of you either blew it off completely or handed it in garbage. Guess what? That assignment was about this. That's why most of you don't know how to do it. Well, watch this video. Hey, put your pencil down. Yeah, that's right. I know you're watching this video because you didn't do your homework. Well, don't copy me. Put your pencil down. Learn it. Do it yourself for once in your life. Do it right. Okay, I got carried away there. First, we'll just graph the log function like we normally do. Starting with the y values, -2, -1, 0, 1, and 2. Okay, it helps to look at the parent function, y is equal to log base 3 of x, because we're going to start by graphing that. But we're working backwards, starting with the y, so it would be helpful to use the exponent form of this. So starting with the base, bring my base down, and then the y and the x, when you change forms, these will change sides. So it'll be x equals 3 to the y power. Now that's telling me how to find these x's. I'm going to do 3 to all the y powers. So that means I'm going to do 3 to the -2 power, and 3 to the -1, and 3 to the 0, and 3 to the 1, and 3 to the 2. Well, because this is a -2, it drops you down, like 1 over 3 squared. So that's going to be 1 over 9. This negative will drop you down and give you 1/3. Anything to the 0 power is 1. 3 to the 1 is just 3, and 3 squared is 9. Is there an a value? Sort of. Well, let's go ahead and say yes. This negative sign right here counts like a -1. So we will have an a value. So as we go from y to a times y, that means we're multiplying all of these y values times -1 because of this coefficient. So multiplying everything by -1 is really just going to change the signs. So this will become +2, +1, 0, -1, -2. Once we have this third column of y values, we can forget about the old one. Excuse me. So we're just going to graph these pairs. This will not be the final answer. So I do my temporary points in green, just how I like to do it. By the way, using colors, very helpful. So I've got 1/9, comma 2. Alright, so that's over almost nothing, and then up 2. And then 1/3, comma 1. So that's over a tiny little bit and up 1, like that. And then 1, comma 0, so over 1, up nothing. 3, -1, over 3, down 1. And 9, -2, so there's 9, -2. So those green dots show the parent function. Do not connect them. But the reason why they are not the final answer is because we have not done the shifting yet. Okay? This +2 right here is going to send us, you know what, let me make it over here. So the original so the original graph has the following shifts. Because of this, I'm going to be going left 2. That's right, inside the parentheses we have left-right motion, and it's the opposite of what it looks. So if it's positive, we go left. Because of this, I'm going to go down 1. Alright, a translation of down 1. Obviously, numbers hanging on the end like this, outside the parentheses, are up down numbers. Negative will be down, positive would be up. So we will do that shifting to these green points, and that will give us the final graph. Left 2, down 1. So here we go. Left 2, down 1. Yeah, left 2, down 1. Okay. Left 2, down 1. Left 2, down 1. Okay, same. And left 2, down 1 right here. Just making these a little bit bigger. Okay, these are the 5 dots we will graph for our final answer. Let's go ahead and get the asymptote in here. Because this is shifted left 2, the asymptote, which normally is on the y-axis, will be over 2 to the left. So check it out. I'm too close. Better. Alright, so there's my asymptote, but I am going to bring it over to the left 2, like I said. Alright, there's the asymptote. Now all that's left is to draw this curve as best we can. Now you see that it's approaching the asymptote like this. So by the time we get up here, it's going to appear to just trace the asymptote, even though we know that it doesn't really touch. Okay, so your graph should look something like this. Now, please understand we are only halfway done. So many of you do this and stop that it disturbs me that you're not reading the directions. It says graph the following log function and its inverse on the same coordinate plane. So we've graphed the original, but now we have to graph the inverse. Before we do that, and confuse the issue with another graph, let's go ahead and put down this information for the graph that we're looking at. First, the end behavior. End behavior talks about what happens on the left and what happens on the right. So first, the left. Okay, as x approaches, alright? That means as we go to the left. By the way, x is approaching not negative infinity. We've got an asymptote here. So the x values are getting closer and closer to negative 2. So as x approaches negative 2, and the question is, what happens to the y values? What are they approaching? Well, as the x values are getting closer and closer to negative 2, the y values are going up, positive infinity. So that's the left end behavior. Now let's do the right. Okay, well, as the graph is going to the right, alright, as the x values are approaching positive infinity, okay, meaning as we go to the right, what happens to the y values? Well, as we go to the right, you see the y values are going down, negative infinity. Alright, now, the x-intercept is not a whole number. It's somewhere between negative 1 and negative 2. And I would say that, in fact, let's see. This seems to be about negative 1.9. Alright, so I will say negative 1.9, 0. Alright, but you can estimate if you need to. Now, the asymptote. Clearly the asymptote is here at negative 2. Vertical lines are always x equals. Alright, so x equals negative 2. Now the domain. The domain is how far it goes to the left and how far it goes to the right. To the left, it stops at the asymptote. So the domain will be -2. On the right, it goes forever. So -2 to infinity. Now the range is how far it goes from bottom to top. Well, at the bottom, this keeps going forever down. So it starts at -infinity. At the top, it goes up into the sky forever. So that's positive infinity. Okay, so there's the vital statistics for the original graph. Now let us do the inverse graph as requested. Okay, now look, the inverse graph, remember how we got these green points, from the parent function? Well, just understand that the inverse graph will have the same points for the parent function, except for the x and y coordinates will be reversed. So the inverse function will have a parent function of 2, 1/9, alright, switching these around, and 1, 1/3, and 0, 1, and -1, 3, and -2, 9. Alright, just reversing each one of these parent function points. So these red values are the ones I'm going to graph for the skeleton function. The parent function. So 2 and 1/9. So over 2 and up almost nothing. Now 1, 1/3. So over 1 and up just a little bit. Okay, 0, 1. So there's 0, 1. And then -1, 3. So -1, 3 would be here. And finally -2, 9. So here's -2, 9. Don't worry that that's right on the asymptote, because this is not the asymptote for the inverse. Alright, the inverse has its own asymptote. So don't pay any attention to this asymptote. Alright, the inverse can cross right over this green line. The inverse, in fact, will have a horizontal asymptote at the same number. So if the log function has a vertical asymptote at -2, then the inverse function will have an asymptote, a horizontal asymptote at -2. Alright, now I am not going to graph the orange dots right now. I'm not going to connect them, just like I did not connect the green dots. The reason why, I haven't done the shifting yet. Okay, they're just the parent function. Now it's time for the shift, but you have to be careful. Okay, inverse. You have to be careful. It's not going to be the same shift as the original. Okay, the good news is it will still involve the same two numbers. So I'm still going to be dealing with 2 and 1. But these words will both change. Let me remind you of how this works. This is the positive side of the y-axis, and this is the positive side of the x-axis. This is the negative side of the y-axis, and this is also the negative side of the x-axis. Now, of course, you know that this is up and this is right, and this is down, and this is left. So what happens is if you want to talk about the shifting that's happening, when you go from the original to the inverse, the two positive words up and right will be reversed. So anything that's said up will become right. And anything that said left, anything that said right will become up. Similarly, the two negative words will be reversed. So anything that was going to be left will become down. And anything that says down will become left. Okay? So, with that in mind, left, a negative word, will switch to the other negative word, which is down. Wait, that's supposed to be red. That's supposed to be red. I said left, which is a negative word, will switch to the other negative word, which is down. Down, a negative word, will switch to the other negative word, which is left. Okay, so when I want to shift the inverse function, I'm going to move the parent function down 2 and left 1. Okay, so watch me work. Look at these orange points. Down 2 and left 1, I say. So down 2, left 1 will be about here. And then, okay, down 2 and left 1. All right. Down 2, left 1 would be right here. Okay, and this would be down 2, left 1. All right, feel like there's one more. Okay. Down 2, left 1. All right, so these red dots show you where the inverse graph is going to be. Now you can see that it's curving in towards the asymptote. The orange horizontal line is my new asymptote. So it's already super close right here. So by the time it gets here, it's going to appear to be tracing the asymptote. Okay. Wow, so the red graph and the blue graph are actually super close together. But you can see they are, in fact, mirror images of each other diagonally. Alright, I'm going to erase this mess. It's bothering me. Alright, anyway, that's it. The blue is the original graph, and the red is the inverse. Okay? I want to see the dots of the parent function. And I want to see the dots that you used when you graphed the final answer. Don't just throw something down. Okay. Now we need to answer these questions. End behavior. Remember, for the inverse, we are looking only at the red, not the blue. So first of all, the left end behavior. As x approaches something. Well, this red goes left forever, so I'm going to say as x approaches negative infinity. Now, what happens to the y values? Well, as we go to the left, it goes up forever. So that'll be positive infinity. Now, how about the right side end behavior? So as x approaches positive infinity, okay, because in fact it does go to the right forever. But as we go to the right, what happens to the y values? Alright, it doesn't go to negative infinity, it flattens out and approaches this asymptote of negative 2. So, as we go to the right, the function approaches negative 2. Alright, notice the similarities between the original end behavior and the inverse. Alright, the y-intercept is going to be similar to the x-intercept. Okay, See the y-intercept right here? But take a look. That seems to be 0, negative 1.9. So it's almost the same, only the x and y's are reversed. What would we have if I switched x with y right now? Well, I would have the horizontal asymptote, y equals negative 2. And that's what it is. The domain, that's how far the red graph here goes from left to right. Well, this goes left and right forever, both directions. So that's going to be negative infinity to positive infinity. And finally the range. The range goes from bottom to top. Now this red, focus on the red, only the red. This graph has a bottom. It doesn't go down forever. It cannot go past the horizontal asymptote at 2. So bottom to top, that's negative. Did I say 2? I meant negative 2. So bottom to top, this red graph goes from negative 2 to infinity. Okay, so that is it for that problem. Okay, number 11. You need $25,000 in 11 years. How much should you invest now at 12.5% annual interest compounded continuously? Round your answer to the nearest penny. Okay? Why did I emphasize this word? Because that's what tells us which one of those formulas we're going to use. Are we going to use this one? Or will it be this one instead? Well, look. This is the formula for interest compounded continuously. So we will definitely use the PERT formula. Y equals PERT. Let's copy that down. So we will start off with the formula. Alright, y equals p times e to the RT power. Now be careful. This 25,000, is it going to go here for the y, or is it going to go here for the p? Alright, you never know. You got to read the problem. But I will tell you this, it will go in for p if the 25,000 is the initial amount. Okay, that's your p value. It's the amount now. It'll go for y if it represents the final amount. Okay, and that's the amount you will have years later. So, which is it? Is this the amount we have now or the amount we'll have years later? If you need $25,000 in 11 years, it's telling us this is the amount we want to have years later. Okay, so that tells me that the 25,000 is going to go in for the y. By the way, just to read on, how much should you invest now? Alright, so they're asking how much we should invest now. That means that's the p value and we don't know it. So we have to just leave p as a variable. Okay, so that's why. Just erase this nonsense real quick. So that's why the $25,000 goes in for y out front. So 25,000. P, I don't know what it is. So E is a constant, so that's definitely just E. But R, got to get that. 12%, this is where the R value is going to come from. You got to move that decimal point twice. Okay, so in this case, R will equal 0.125. Okay, so this will be 0.125. Now, so that's R. Now comes T. T stands for time. And don't say 1 year because it says annual. It's how many years are going to go by. you need $25,000 in 11 years. So that means the t is in fact 11. Okay, now do not try to evaluate this and then divide later. Divide now. So you would do this. Trying to get p by itself, right? So you will divide both sides by e to the 0.125 times 11 power. Both sides, e to the 0.125 times 11. That way, all of this will cancel out. And you'll just be left with p. You know what, I'll bring it over here. Alright, by the way, on test day, you will not be allowed to use your TI-30 XS multiview. So, on a problem like this, you know how this is what we will put in our calculator? Well, if you don't have your calculator, just write this down and that'll be your final answer. Okay, that would be your answer right there. But since I do have a calculator, I'm going to go ahead and use it. Okay, so I've got 25,000 over e to the 0.125 times 11. Okay, so I need $6,320.99. That's how much we need now at this particular interest rate if I'm going to have, hold on, $25,000 in 11 years. Anyway, that's the final answer. Number 12. Okay, these are the ones where they give us certain values. This time we're given 8 and 7 and 10. Okay, let's write everything with 8s and 7s and 10s. 343. Let's consult the chart, shall we? 343. Oh, look, 343. That is 7 to the 3rd power. Let's use that. Now 7 is one of the numbers I know, so I like this. Please remember that I can just take that 3 and put it in the front. So that'll be 3 times the log base 5 of 7. Now we know that the log base 5 of 7 is 1.21. So this would just be 3 times 1.21. So that's going to be 3.63. So that is the answer to number 12. Number 13. We're going to have to use our laws of condensing and stuff. I see the 7 that I want, but I need a 10 and I could use an 8. Looking at the 80, how in the world could I ever get an 8 and a 10? That is a great idea. Let's do log base 5, but in the numerator, why not do 8 times 10 to make 80? Now, notice that I have 3 factors here, 3 of them. That means when I expand this, I'm going to have 3 log terms. Anything in the numerator is going to give me a positive term, and anything from the denominator will give me a negative term. So I should have 2 positive terms and a negative term. So here we go. I'm talking about log base 5 of 8, positive term, plus log base 5 of 10, another positive term, minus log base 5 of 7. Only a negative term because it comes from the denominator. Now, all three of these facts are facts that we are given. Alright, the first one is 1.29. The second one, with the 10, that's 1.43. And then the last one is 1.21. So just do these two at a time. So if I put these together, it's going to be 2.72 minus 1.21. And that's going to be 1.51. Okay, that's the answer number 13. Finally, number 14. Well, 700 could be written as 7 times 100, right? Now, you can either do 100 as 10 squared or 10 times 10. So I'm going to do it this way. So that's to be 7. Now 100 is 10 times 10. I could have done 10 squared and put the 2 in the front if I wanted to. But done this way, I have 3 terms, all positive. So I will have log base 5 of 7 plus log base 5 of 10 plus log base 5 of 10. Well, log base 5 of 10 is 1.43, so I've got plus 1.43 plus 1.43. Log base 5 of 7 is 1.21. Got to add it all up. Okay, so putting these two together, I've got 2.64. Okay, plus 1.43 is 4.07. Alright, that is the answer to number 14, guys. Alright, number 15. The value of the variable in each equation. Alright, all of these are going to involve rewriting into exponent form. Start with the base. If I bring down this base of a, and then everything else will change sides. So this negative 3 is going to come over here and become the power. And then this is going to come over here, 1 over 512. Now, here's the trick. I'm trying to get a by itself. The way to get rid of negative 3 is to use the reciprocal power. The reciprocal of 3 is 1/3. So I'm going to do negative 1/3 power. Have to do it to both sides, okay? Negative 1/3 power. The reason why I did that was if I do the reciprocal here, everything cancels out. So I will just get a. And that's what I wanted, a by itself. So all I have to do is evaluate this and I'm done. Well, if you have a fraction and a negative power, you do the reciprocal. So the reciprocal of 1 over 512 is just 512. So now I have 512 to the 1/3 power. Well, remember that the 1/3 power is the same thing as the cube root, third root. So hopefully that's just sitting right on our chart. Okay, cube root of 512 is 8. So just plain and simple, the answer is 8. Booyah, Jim. Okay, number 16. Once again, first thing I'm going to do is rewrite this in the other form, starting with the base. So our base is 1/27. Now the rest of this will trade sides. So this 4 over 3 is going to come up over here and become the 4/3 power. Okay, the x is going to come over here and be x. All I have to do is simplify this somehow. Now look, if you take this 1 over 27, okay, I'm just going to break this down for you. This would be the same thing as doing the 4/3 power to the 1 and to the 27 separately. Okay, that's important because doing any kind of a power to a 1 is just going to give you a 1, right? So this is just like having simply 1 over 27 to the 4/3 power. Now, do you guys remember that when you have a fraction like this, the top number is the power and the bottom number is the root? So that means what I'm really looking at here is the cube root of 27, alright, because the bottom numbers are 3, that's your cube root. And then all of that will be raised to the 4th power, alright, it's power over root, 4th power. All I have to do is evaluate this and I'm done. Now I can do this whole thing in my head, but I'm going to walk you through it. The cube root of 27, okay, cube root of 27 is 3. So that means that I've got 1 over 3 to the 4th power, alright, because this in here is 3. But 3 to the 4th power, I know what that is, 2. 3 to the 4th power is 81. Alright, that's why this denominator is 81. And the final answer is 1 over 81. Okay, where are we doing? Alright, number 17. Alright, one more of these. Once again, we can rearrange this in exponent form, starting with the base. So I have a base of 125. Now the 5 and the n will trade places. So I have 125 to the n power is equal to 5. Alright, this is a very simple version of what we've already done before. 127 to the what power will be 5. Well, you got a bigger number going to a smaller number, so you can bet it's going to be some type of a fraction. Okay, in your mind at least, think about what kind of root would do this. Okay, will it be square root, third root, fourth root? Let's check the chart. Look on the 5 row and look at the 125. Okay, there's 5, there's 125. So that's 5 to the 3rd power. That means the cube root of 125 is 5. Okay, so that means the cube root of 125 is 5. Well, cube root is the same thing as the 1/3 power. Alright, so the 1/3 power will change 125 into a 5. That's why that's the answer, number 17. Alright, I think this is the last one. The triple decker. It's not so hard if you take it in bite-sized pieces. Okay? I will call this piece right here, I will call it P. Now, I will call this larger piece right here, okay, I will call that Q. I'm doing that to make my life easier. Okay, this is just too much for me to hold all in my head at one time. So let's just look at the outer function, log. Okay, so for starters, I have this. I have the log of, now the rest of this, everything I'm highlighting in yellow, all of that is Q. So really I just have the log of Q. Alright, so the log of Q is equal to 0. Now, don't forget the invisible base here. Alright, this is invisible base 10. go ahead and write this in exponent form, starting with the base, the 10. If I bring that down and switch these around, then I'll have 10 to the 0 power equals q. Okay? But anything to the 0 power is 1. Okay? So that gives me the value of q. Now, let's start from here. So, here's what I know. I know that q is equal to 1. Alright, now let's go ahead and put back in what q really is. Q is everything highlighted here in yellow. So all of this stuff in yellow should equal 1, because that's q. So that means log base 3 of log base 4 of x, all of that yellow stuff should equal 1, because q equals 1, and that's what q is. Okay, but now we have to break it down more still. So we're through with q. We found q. Now at the next level, I don't like having this log within a log. It's still too hard. So let's go ahead and replace the log base 4 of x with p. So that means this log base 3, okay, because all of this stuff in here, that's p. Okay, see how they're the same? Ha, that looks like 1 over p. I better not do that. Maybe I'll put it off to the side. Yeah, that's p. So that's why this is really log base 3 of p is equal to 1. Alright, writing this in the other form, starting with the base. So there's my 3, and then these two are going to change sides. So I've got 3 to the 1 power is equal to p. Okay, so obviously that means p is equal to 3. Alright, so once again, let's start from there. Let's start from the fact that p is equal to 3. Let's always start with what we just found. Okay, but remember what p is. P is everything highlighted here in yellow, log base 4 of x. So let's make that substitution. Let's replace p with what it is, log base 4 of x. Alright, that means log base 4 of x should equal 3. Alright, just bringing that down. So our goal was to find x. So let's just do this one more time and do exponent form. So bring down your base of 4, and these two things will switch sides. So that's 4 to the 3rd power is equal to x. Alright, 4 to the 3rd power happens to be 64. So that will be the final answer. Okay, 4 to the 3rd power is 64. And that is it for this review, you guys. I hope it was helpful to you. And I will see you on the next video.